So, hello everyone. I am Varun, and I, along with my colleague Ashish, will be presenting today's paper. And the name of the paper is Language-Driven Semantic Segmentation. Right. So, before we actually take a deep dive into the paper, okay, it's important to know like what image segmentation is, right? Okay. So the first slide, okay, talks about different kind of things which are possible with image, right? For example, like object detection. I think like most of you would be familiar, right? Object detection is pretty straightforward as this picture explained, right? So object detection is having a bounding box around each object. Okay? It can involve like detecting single objects or multiple objects, right? And the segmentation, okay, segmentation is different from object detection in the sense like segmentation is of two kinds. Okay, one is instant segmentation and other is semantic segmentation. Okay, instant segmentation essentially identifies boundary of object and label its pixel with different colors. For example, if you see the image on the slide, right, so there are a picture of two dogs and cat, right? So instant segmentation is successfully able to identify the objects, okay? And it's also able to identify the boundaries of the object, right? And label the pixel with different colors. So it says like there is a red dog. It basically labels one dog as red, other dog as green, and the cat as the blue color, okay? But the thing which we are going to discuss in this paper is semantic segmentation. Okay, semantic segmentation, on the other hand, works at pixel level. Okay, and it doesn't work at the object level. And the aim is to assign a label to each pixel in the image. Okay, so it does not differentiate between two instances. For example, if you see the current picture, okay, there are two cows, right, and then there is a background of grass, sky, and other things. So essentially, like it has um, categorized, okay, both the cows as a category of cow, right? It's not differentiating between the instances. Okay, this is important difference to note when we talk about semantic segmentation. Okay, let me see if there is something. Okay, so now let's move forward. Okay, like just 1 second, yeah. So let's deep dive into like semantic segmentation, like what exactly is semantic segmentation, right? So idea, okay, is to classify a certain class of image and separate it from rest of the image classes by overlaying it with segmentation mask. Okay, and this is done by assigning a semantic class label. So if you see the picture right now, right, so it has a lady, okay, it has a purse or a bag, right, and it has some background, okay, in which we have a pathway, right, we have grass, trees, right. So and if you see on the right side, okay, what exactly semantic labels that have been assigned, right. So it has basically taken a few categories, okay, and it has assigned each pixel, okay, into different categories, right. For example, like it has assigned the lady into a label of 1, okay, and if you see, okay, this is how it has segmented it, right. So this portion of the image, it has masked it, okay, uh, as 1, okay, so that's what class label it has assigned, right. And similarly, if you see 3 corresponds to the grass, okay, and so it has assigned that label, okay, and so on and so forth, right. So this is more about like how what exactly is semantic segmentation, right. Okay, let's move forward. And now we know, okay, what is semantic segmentation, right. So now the question that comes up to mind is like English language, right, have several hundred thousands of nouns, isn't it? So then why is that so, like we have only a limited set of semantic class labels assigned to pixels? That like if we have several 100,000 nouns, okay, so we expect similar, like several 100,000 semantic class label assigned to pixels, isn't it? But that's not the case. Okay, usually the range is only from 10 to hundreds, right? So why is that? So like why do we have so less semantic class labels assigned to each pixel, right? So the challenge in this whole process is that like there are about like thousands of images, right? And every single pixel has to be manually annotated, isn't it? And that is something which is an extremely laborious task. Okay, and for the larger data sets, okay, like we can have fine-grained candidate labels, isn't it? Like in the sense like each label can be again subdivided into much more fine-grained labels, right? If we have a larger data set, so that's also increases complexity, isn't it? And then there can be cases when like different descriptions are possible, isn't it? For example, like in the image before, okay, like the background pathway can be described as pavement. Someone will say it's a road, right? Someone will say it's just a pathway. So essentially, like inter-annotator agreement becomes a problem, right? So these are all challenges, okay, which comes forward when we try to assign a lot more category to the pixels. Okay, so what is the potential remedy, isn't it, to this problem? So in the past, two popular approaches have been tried. Okay, few shot approach and zero shot approach, right? So a few shot and zero shot approach is not specific to this paper. Okay, that is something which is commonly used when we talk about like machine vision and even now in NLP, right? So idea is like uh, to segment the new classes, okay, based on only few labeled images. Okay, that's the idea, right? So it's not like you would be expecting the model to be trained with a lot of um, classes, like a lot of instances of the classes, okay, but only few. Okay, but it still requires label data, and it requires the label data to have those new classes. The zero shot approach, okay, tries to take the things further, okay, and the idea is to segment unseen objects without any additional samples of new classes, right? So there is, it's like you basically have never shown your model during training time, say a label called dog, right? And you expect at the testing time, okay, when you are inferring, you expect when you show it a picture of dog, it should be automatically able to label it as dog, right? So there is something called a zero shot approach. We have never, it's kind of an unseen object which you are trying to show at the testing time, okay? And usually, okay, for zero shot approach, word embeddings are used, right? And it's not something which has been tried only in this paper. Like word embeddings are used, and the idea is that it projects visual features into a simple word embedding space, isn't it? And then it correlates the resulting embedding to assign a label to pixel, right? So yeah, so these are the two kind of approaches which have been tried previously to come across the problem which we discussed before. So how is this paper different then, isn't it? Like we are talking about zero shot approach being tried before, we are talking about word embeddings being used before. So how is this paper different, right? The focus of this paper is to bring together zero shot semantic segmentation models by using high capacity language models. So if we see this paper, okay, it's not like it's has developed a new model of its own, okay, like it's kind of combining, okay, state of the art language model and image models together, okay, and the idea is to achieve a very good accuracy on the zero shot settings. Okay, that's the whole idea of this paper, right? And it basically tries to generalize, right, segmentation model much more strongly, okay, by using a language, right? By basically using the language assistance, it tries to improve the robustness of the segmentation models, right? And we will see later in the slides that the result, okay, the resulting model has outperformed the existing zero shot settings, and it has also got a very competitive scores for a few shot benchmarks, but that we will see later. Okay, so now let's talk about the framework, isn't it? So idea is like it uses the text encoder and image encoder. Okay, and again, the high level approach is to embed the text labels and the image pixels into a common space and assign the closest label to each pixel as shown in the diagram. Okay, so this diagram is showing the same thing, like there is a text encoder and the text is coming, and there is an image. Okay, there is also getting embeddings are getting generated for the image as well. Okay, and then idea is to have them in a common space, and finally like assign a closest label to the pixel. Okay, so we will decompose this diagram block by block and study about each of them as we move forward. Okay, this is at a high level. Okay, now let's talk about the first block, right? So now let's talk about the text encoder, right? So the text encoder used here is clip VIT-B32, okay? And so what these they have done essentially is like they have reused, okay, the text encoder from clip, okay? And if you study the paper which introduced clip, okay, they also basically trained this text encoder along with the visual data. Okay, so this was done previously in the clip paper. Okay, and why they call the text encoder as clip VIT-B32, isn't it? Like the idea is like when actually clip pre-training was done, okay, then it was basically used in conjunction with the VIT-B32 image encoder. Okay, that's why they call it like the text encoder is called like the clip VIT-B32, right? And again, like the idea is to transfer the flexibility of the text encoder to visual recognition. So for example, like a dog is closer to pet, isn't it? And it's not closer to vehicle. That's one example, isn't it? Like, and this is the whole idea of embeddings, right? If you see in NLP also, right? You have basically the idea is to have similar words, okay, closer in the vector space, right? So this is more of text encoder, and this is more of like classical NLP how it works, right? So okay, later on, what we will see is like they have also used some other encoder, okay, apart from the clip VIT-B32, right? They have used some other encoders as well, and this table basically shows like which different encoder they have used. And the main difference is like the image encoder, okay, that was paired when the clip pre-training was done, right? For example, like if this table, if you see, right, there is a VIT-B16 text encoder being used, right? So this essentially like indicates that during the clip pre-training, okay, this particular text encoder was used in conjunction with VIT-B16 image encoder. Okay. The other difference which to be noted is of the embedding. Okay, like in the sense, the size of the embedding dimension. Okay, that's important in the sense like if you see 512, 512, 640, and 768, isn't it? So that essentially is like your size of the dimension. Okay, the dimension of the vector, isn't it? And one thing important to remember here is like the text encoder, okay, feature the same transformer-based architecture, okay, that purely operates on text, isn't it? So although like they are actually borrowed from clip, okay, and they were actually trained alongside the image encoder, but the architecture, okay, is purely like a transformer based architecture and purely operates on text. Okay. Similar to the text encoder, right, we have image encoder. Okay. And image encoder basically produces embedding vector for every pixel instead of the text, right? And here they are using something called as dense prediction transformer, DPT. Okay. And this is a segmentation model, okay, that was released by Intel in March 2021. Okay, and it applies vision transformer to images. Okay, and the training is done in such a way, okay, that uh, it maximizes the correlation between the text embedding and your image pixel embedding. Okay, that's the whole idea, like how closely you can correlate them, right? But the question essentially is like how is this correlation obtained, right? How are we able to uh, obtain a very good correlation between the text embedding and the corresponding image pixel embedding? So let's see that. So what happens is like there is something called a word pixel correlation tensor which is created. Okay, after the image and the labels are embedded. Okay, correlation is done using the inner product. Okay, creating a tensor, right? And during training, okay, image encoder is kind of encouraged to provide pixel embeddings that are close to the text embedding for a particular class, right? And how is this done, right? Like for any machine learning problem, right, there is something called the loss function which is minimized even. So this is same here in the sense here per pixel softmax with cross entropy loss. Okay, and that is something like which you get it from PyTorch, right? So PyTorch cross entropy loss function is minimized. Okay, and this is kind of a standard in semantic segmentation, which is followed across um, all the semantic segmentation models. Okay. So after doing all this, okay, there is one problem, and that problem is like due to the memory constraints, right? The image encoder predicts pixel embeddings of lower resolution, okay, than the input image resolution, right? So you have done the image encoding. Sorry, you have done the image encoding. Yeah, you have done the text encoding. You have done the correlation, but finally, okay, like what image encoder, like what we get out of uh, all this is image, okay, which has a lower resolution than the input image resolution, right? So what is done for this is basically there are two post processing modules which are proposed. One is like the depth wise block and other is the bottleneck block. So this is shown in the picture, right? uh, Essentially depth wise convolution is followed by non-linear activation. So in this diagram on the left side, you can see like a depth-wise convolution is followed by a non-linear activation, right? And in the right hand side image, okay, which is called the bottleneck block, similar model is used, okay, but additionally, okay, it is augmented uh, with max pooling operation. Okay, so if you see the only difference between these two uh, right kind of thing is like you have a max pooling operation also augmented with the depth-wise block, right? So just to digress a bit, isn't it? Like what exactly is depth-wise convolution, right? So um, essentially, like what happens is like you would have heard like a regular like a 2D convolution, isn't it? But in the depth-wise convolution, essentially what happens is like we split the input and the filter into channels, okay, and we roll each input into a respective filter, right? Idea is like we keep each channel separate, okay, and to apply like a single filter for each input channel. Okay, like in a regular 2D convolution, okay, like it allows you to freely mix channels, isn't it, to generate output, right? But in depth-wise convolution, okay, it's quite uh, it's followed, okay, to keep the channel separate. It's not allowed to basically mix the channels. So yeah, that is something which is depth-wise convolution. But yeah, so essentially these post-processing modules are required because we need to recover the original image resolution. Okay, that's why these post-processing steps are required. Okay, now talking about the training details, right? So for the training details, the weight initialization is important, isn't it? So weight initialization for encoder backbone, okay, is done using ImageNet pre-trained weights from VIT or from ResNet2. Okay. Now here, like for people like who don't know, like backbone in the sense, like backbone here refers to the feature extracting network, right? And it's kind of like why it's called backbone is because it's kind of the essence, okay, like to encode the network's input into certain other representation. So yeah, so the weights initialization, okay, is done using ImageNet pre-trained weight, and for the decoder, okay, when it comes to decoder of the DPT, the weights are initialized randomly. Okay, and there is one thing is which I noticed in this paper was like the training is done such a way that the text encoder is freezed, right, and only the weights of the image encoder are updated, and so on. So because essentially like you are trying to deal with text encoder as well as the image encoder, right, during training. So they do in such a way that they freeze the text encoder and they only update the weights of the image encoder, so on. So this was at a high level, this was about the training detail. Okay, so here what I tried to do was basically like bring together, okay, all the like kind of a mat, okay, which is happening behind the scenes, isn't it, in one slide. Okay, so essentially like what happens is like you have a set of n labels, isn't it, which is in your data set which you want to train your model on, and you use the text encoder, right, to create a vector called like a T, isn't it? Here they call it a vector T, and then there is an image, okay, and image size suppose is h into w, right, height into width, and s is like a down sampling factor, okay, and essentially what we do is like we create h and w uh, by actually dividing by the downsampling, right, and so this is like fed into the image encoder, and finally you get a dense embedding matrix like I, okay, and so then we talked about correlation, isn't it? So essentially what happens is like a correlation tensor is created by multiplying, okay, by using a dot product. So what is happening is like of the size h into w into n, where n is your potential labels, right? So uh, you get a tensor, okay, f here in this it's shown as f, right, and then yeah, the one of the aim is to actually maximize this dot product, right, and then the training is done in such a way that we minimize the per pixel softmax with the cross entropy loss. So this is shown here, like the loss function, okay, how it is essentially used in the model, okay, and like each epoch it would be of the training, it would be minimized. Yeah, so this is again like at a high level the math behind what is used in this model. Okay. Okay, so now I would probably hand over the presentation to my colleague Ashish.
Yeah, sure.
Ashish, are you there?
So can you please stop sharing?
Yeah. stop sharing and you can take over from.
Okay. Okay. So are you able to see my screen?
Yes, we can see.
Yes,
Okay.
yes.
Okay. So moving on to the next topic, let's summarize what are the points already covered by Varun. So the first one is the classification, then detection and the segmentation. So next one is how label resizing works. After that, the next is challenges faced for the segmentation work. After that, some sort of literature review, or we can call it as a potential remedies. That is a few shot and zero shot approach. After that, language segmentation framework. After that, text encoding, image encoding. At last, the maths behind the model. Let's move on to the next topic, that is experiment. So here in language segmentation, zero shot and for few shot semantic segmentation models on a few short benchmarks, there are a lack of standardized protocol and sufficient data sets. So and baselines for the zero shot setting are available. So here there are some three protocols. Recent the state of the art, we can say few shot method, that is HSNet, and evaluate on three widely used few shot semantic segmentation. First one is Pascal 5, second one is Coco 20, and the third one is FSS 1000. Moving on to the all these three benchmarks, let's discuss what is here we have used here they have used HSNet, that is a state of the art few shot method. In that, the two protocols, the standard protocols they have used, first one is a mean intersection over union, that is MIOU, and the another one is FBIU, that is foreground background intersection over union. Okay, so Pascal 5, it is created from Pascal VOC 2012, whereas in the Coco 20 is created from Coco model. In For Pascal 5, it contains 20 classes. We can call it as a 5i, where I belongs to 0, 1, 2, 3. And for Coco 20, here the classes are more as compared to the Pascal 5. Here there are 20 classes having four folds for each class. Okay, so the accuracy which we got from which they have got from the backbone they have used is ResNet 101, is something sort of like in FBIU, that is 77.6, whereas if you use language segmentation, it's quite it's low as compared to the ResNet backbone, that is 67.0. For Coco 20, it's relatively high as compared to Vision Transformer L16 in Pascal 5, that is nearly up to 69.1. For let's move on to the third benchmark, that is FSS 1000. It contains both unseen and annotated image objects. Here the main goal for the FSS 1000 is object classes are more emphasized as compared to the data size. So training is divided, so 1000 classes are divided in such a way, training is of size 520 classes. For validation it's 240, and size is also 240. So the accuracy, we can say, from MIU, it's relatively high as compared to the Coco, it's 87.8. Here also we have they have used Vision Transformer L16. So these are the outputs which came from, if we use FSS 1000. So for qualitative analysis, here it is trained with 7 different data sets. The first one is AD20K, second one is BDD, third one is cityscapes, then Coco Panotic, IDD, Mapillary Vistas, and Sun RGBD. So if we see over here in left side, labels that are hello.
Yeah, Ashish.
Okay. Yes, yes. So labels that are removed between runs are underlined here, like a house or the plant.
Your voice is breaking, Ashish.
Yeah, Ashish, we can't hear you if you're talking. There's no sound.
Perhaps he's having some connection issue.
Yeah.
Yeah,
Oops, yeah.
I
Well,
think we have lost.
in the meantime, I have a question is, do you have an example of how a training example looks like? I am curious about it. I suppose it has a class per pixel, right? Is it a huge file with a JSON file for each example?
Unfortunately, even like we could not run the code. Okay, like we tried. Okay, but the kind of PyTorch version it requires. Okay, that was not compatible. I tried multiple options. So yeah, we could not run the actual code. But yeah, we can get back to you on that maybe after some time. Like we are able to run it.
So thanks,
The,
sure.
the input is generally a polygon for any class. For example, you are creating a tree, so you can create a polygon of tree. And so anything inside that closed polygon will be one class. That's how the training can happen. And generally there are two inputs. One is the polygon that is level, and one is the image.
Great, thanks.
Oh, sorry for the inconvenience. Okay, so we're talking about this building image. So in the first row, if we see on the left, we first start with a label that is set sky, road, house, and plant. After, if we run this model, in that, if you observe that model is capable of segmenting the image into the product classes, right? If we change the house to the building label and the plant with greenery, the model produces the similar segmentation as before on this different but semantically related label set, we can call. This is despite that the fact that the model greenery or even green was not present in any of the these training samples or the training images. Now for the second row images in related unseen labels, if you observe that similar effect is shown in the second row too, where language segment successfully segments the image and correctly assigns the labels. Here we change the cake label to the desert.
Why is it breaking slowly, Ashish? Maybe you can try to speak a bit slowly.
Okay, okay. Okay. So
I don't
here
so,
we change.
sorry, but I don't think we can hear you properly. There's a lot of disturbances.
Now am I audible properly?
Yeah.
Okay. So here we change the label from the cake to the desert. It's showing the same output, whereas desert was not seen during the training, while successfully suppressing the label bread here, which is both visually and semantically related. Okay, so moving on to the next, this is hierarchical unseen labels. Here the model is able to recognize the cat, or we can say plant, and grass segments of the image as expected, since these labels are present in the training set. When replacing, we replace the cat with a furry and grass with a plant. The model is able to successfully recognize the parent category, that is furry. On the same side, this in second, that for the sofa and other objects, however, the small shelf on the left.
Again, Ashish, lot of disturbance.
Yeah, the voice is distorted, Ashish.
Yeah.
Wait.
Perhaps Ashish can talk and Barun
Maybe,
can share the
yeah.
screen.
Yeah, I think so. Let's try that. Okay, I'm going to present. Ashish, I'm going to present. Okay. Ashish, are you with us?
Now?
Yeah. So maybe can you see my screen? Like I'm presenting.
Okay. Yes.
So yeah, you can maybe just. Yeah.
Okay. So in hierarchical, this in sofa's image, if we see when we change the sofa to the furniture, the language segment successfully identifies both the sofa and the small shelf that is as furniture. Okay. So one thing to note is furniture never appeared in the training level set. That's means the language semantic model in general.
There's a lot of disturbance.
Now?
Okay, yeah. Let's give it a try again.
Okay. So language segmentation in generally achieves the very groundbreaking results, but we also observe some failures cases. Let's move on first the strengths. The model can be trained on any, we can say, semantic segmentation dataset. It supports multiple types of dataset like unnamed or the unlabeled, sometimes unlabeled dataset as well. Means it supports flexible mixing of multiple datasets. And next is language segmentation can dynamically handle label sets with varying length, content, and order. This is done by using the embeddings. This property allows using zero-shot segmentation, where the data set is not that much labeled as compared to the few-shot embeddings or the few-shot semantic segmentation, by simply changing the labels that are tied to the text encoder. Okay, so there are some limitations as well. Whenever we go for some advanced, hello.
Ashish, again, lot of disturbance. Okay, I think only one slide is remaining. So maybe.
Yes.
Okay.
So now,
Yeah.
it's fine.
Yeah.
Okay. I will go slow by slow. Okay.
Okay.
So in this specific example, the model assigns the label toy, since the visual feature of that dog are apparently closer to the toy, right? So than to the grass, whereas in the embedding space, there is no other label that can explain the visual features. So that's why they have the model chosen the toy, whereas it is dog. Another here in second example, the model focuses on single most likely object when multiple explanations are like we can say consistent with the label set. Here the windows of the house are labeled as house instead of window, even though the labels of window is available as a choice for for house windows. So the future work could involve augmenting with dealing with negative samples as well, because for this language segmentation model, they haven't yet used the negative samples for that. So now the demo part.
Yeah. Okay. So I think yeah. So that's it from the slide point of view, right? So let's just have a like a demo which we have published by the paper publishers themselves. Okay. So I will just play it. Okay, and it will basically give you a good idea of like what is happening. So they take a dog, right, and they provide two labels, other and dog. You should see it as correctly identified. And they add another label, tree, which again it is correctly identified tree. And they replace labels and show. So this is example of zero shot, right? So you don't have the label during training. Okay. So this was the demo which was recorded. Okay, so that's it, I think, from our side. And yeah, that's it from our side.
Thank you.
Thank you so much.
Thank you.
Yeah, that was great.
I have a quick question. I guess it's an